We were on longitudinal waves. We made some primary definitions.
Assalamu alaikum, sir.
Wa alaikum assalam. So longitudinal waves, we started that. We first made the definition. We had written that a wave in which oscillations are parallel to the direction of the waves. When a longitudinal wave travels, it's a sequence of compression and rarefaction. What is compression? Compression is a region of high pressure, while rarefaction is a region of low pressure. So when particles are moving towards each other, it is called compression. So I think so we had copied it till here, but you people can check for me. And so compression when a longitudinal wave travels, it is a combination of compression and rarefaction. What is a rarefaction? Rarefaction is a low pressure region.
Should we copy this?
Yes, you have to copy this screen. The second concept for today would be the idea that a longitudinal wave is a combination of compression and rarefaction.
Done, sir.
Right. Ariba, have you copied it? Noor also?
Yes, sir.
We had started this topic and we had started longitudinal waves in our last class. Before that, the chapter was dealing with transverse waves. In a transverse wave, the oscillations are perpendicular to the wave, but in a longitudinal wave, oscillations are parallel to the wave. Examples of longitudinal waves: sound waves, shock waves, waves in a spring. You have to copy this.
Done, sir.
This is a spring, a series of compression and rarefaction. Look at this animation. It's a very nice animation to understand what is a longitudinal wave. Another very good animation. If you very carefully see, every particle oscillate on its mean position. The pulse travels along the wave. Look at the pulse.
Yes, sir.
When a longitudinal wave travels, there are compressions and rarefactions. Thus, at the center of the compression, the displacement is zero. At the center of rarefaction, displacement is zero. At the point where compression is changing to rarefaction, here, the displacement is maximum. This is how you can convert compression rarefaction into a displacement distance graph. Normally, the longitudinal wave travels with the wave. The particles oscillate parallel to the wave. So right under it, in a longitudinal wave, displacement in a longitudinal wave, displacement changes along with compression and rarefaction. Now I have marked the points here. First, we talk about points A and B. At A and B, displacement is equal to 0. Look at this diagram. Displacement is 0. It is either the center of compression or the center of rarefaction. Now copy this.
Done, sir.
Answer.
Good. Now we talk about P and Q. Look at this graph again. At P and Q, the displacement is maximum. And when this happens, when compression is changing to rarefaction, look at this position, this one, or rarefaction is changing to compression. So when compression is changing to rarefaction, or compression is changing to rarefaction, at these positions, the displacement is maximum, maybe positive maximum, maybe negative maximum. So we are talking about our next concept here, that this is a point, sorry. This is the junction of compression and rarefaction. You have to update the same screen.
Done, sir.
Done, sir.
So we made a concept of displacement against distance graph. Let's put our next concept for today. A longitudinal wave is like a pressure signal. That is why if you are fond of listening loud music, you will notice that some people do not like it and they feel a pressure on their ear, on their head. Actually, longitudinal waves are pressure waves. In a longitudinal wave, pressure changes periodically. You have to copy this screen.
Done, sir.
Done, sir.
This is called a pressure signal. The x-axis is the atmospheric pressure. The signal goes up, pressure increases, and the signal goes down, pressure decreases. So pressure fluctuates with time. So after copying, you have to copy this pressure signal.
Done, sir.
In a longitudinal wave, pressure increases and then decreases. It's a cycle of pressure. C stands for compression. C stands for compression. And R stands for rarefaction. Now give the heading sound waves.
Done, sir.
Done, sir.
Look at this diagram. Look at this animation. This is a tuning fork and it is vibrating. Sound waves are produced by vibration of a source. Sound waves are produced by the vibration of a source. So give a side heading introduction. And right under it that sound waves are longitudinal waves produced by the vibration of a source. For example, we talk to each other, so we have a vibration in our vocal cord. This sound box, this is actually a vibration. When a guitar sound is heard, how the sound is actually produced by the vibration of a string. You have to copy this.
Done, sir.
Done, sir.
This is a tuning fork. When a sound source vibrates, look at this vibration, tuning fork. When it is vibrating, it will produce a series of compression and rarefaction. So you have to copy this screen now.
So do we copy the entire diagram?
Yes, the whole screen.
Okay. Done, sir.
Good.
Done, sir.
So these are longitudinal waves, conventional longitudinal waves. So sound waves are longitudinal waves. The lambda is the center of compression to compression. From the center of compression to another separation, another compression is wavelength.
Sir, can we have 5 minute break for prayer?
Sure, sure. We stop here for a 5-minute namaz break.
Swinging a door inward produces pulses of increased density and pressure called condensations. Pulling the door outward produces pulses of decreased density and pressure called rarefactions. Within a certain frequency range, such a longitudinal wave of alternating pulses of increased pressure condensations and reduced pressure rarefactions is the wave pattern of a traveling sound wave. Swinging a door inward produces pulses of increased density and pressure called condensations. Pulling the door outward produces pulses of decreased density and pressure called rarefactions. Within a certain frequency range, such a longitudinal.
So this is a concept of compression and rarefaction. Let me know that if you people are back. This is another good animation to understand the particles are, the wavefronts are colliding with each other. Give the heading
Okay.
audible frequency range. This topic is coming from our O-level knowledge, audible frequency range.
20 hertz to
20,000 hertz.
yeah.
It is the wave band. Frequency range can hear a sound. So this is our listening range. So luckily we can't hear everything, and that is why we can comfortably sleep. We can work we can concentrate on our work. So it's a miraculous design that we do not hear everything. This number is famous, 20 hertz to 20,000 hertz. If the frequency is below that, it is called infrasonic. We can't hear it. If it is above 20 hertz, 20 kilohertz, we can't hear it, and we call it ultrasonic, ultrasound. You have to copy this screen.
Done, sir.
Done, sir.
Right. So now give the new heading. Determination of frequency of sound by a CRO. This is something we discussed when we were doing our first chapter, physical quantities. Then CRO was there. CRO was in our O level also. But this is a far away chapter. It comes here because of this topic is here because the waves are the most common subject for CRO. You have to copy this. Give this heading, our new heading.
Okay, sir.
I want to put my chapter 1 memory. This is our CRO. A CRO has two controls, X and Y, and the vertical horizontal shift. We attach a CRO. We attach a CRO with a microphone, and there is a loudspeaker with a signal generator. We call it design question. What is a design question? Actually, they are not very common in AS, but this is a type of question like in our O-level physics ATP was, there was a question like that. This question explains a procedure for an experiment. Like this is an example, this is a CRO, and you want to find the frequency. This is another example. I hope you remember that you have to count the number of divisions, and you have to multiply with the given scale. I would like to just quickly recall, this would be enough that if you get a trace on the CRO, like this is a trace, how we used to solve it. But first, after giving the heading, copy this diagram.
Done, sir.
Rima, have you copied it?
Yes, sir.
Noor, have you copied it? So this is in general apparatus, and this is called a design question. What is a design question? Design questions are like our O-level physics ATP question, where we have to make an apparatus. Now, as I had done this topic with you, so I will give a reference here. I won't go for any writing again. I just had to make that apparatus. So right under it, refer to CRO chapter 1, right under it in a bracket, refer to refer to chapter 1. See out.
Done, sir.
So this was our topic. We had a concept, count the divisions for one cycle, multiply with the scale, you will get the time period. Comparison between transverse and longitudinal. This is an oral discussion. Look at the first diagram, transverse, and the second longitudinal. What is the difference between a longitudinal and a transverse wave? At the closure of this transverse and longitudinal, I want to show you this animation. I have a question to ask now here. What is the difference between a transverse and a longitudinal wave?
A transverse wave vibrates parallel to the direction of wave motion. And
Oscillations, right? The
yeah,
oscillations are parallel to the,
wave motion.
yes.
Along with
This is the difference between them. Now, this is a very interesting topic, polarization of waves. This is the most dangerous topic in our syllabus after 2D momentum. In our syllabus, there are some red topics. Red topics means dangerous topics. 2D momentum, Kirchhoff rules, polarization. These are some dangerous topics in our syllabus. So copy this screen and mark it difficult.
done, sir.
Right.
Done, sir.
Not in syllabus from 2016 to 2022. It was not in the syllabus. Now it is back from 2022. So syllabus history. I put the first concept. When you switch on a light in a room or a car headlight, you will notice that the light will spread out in all possible direction. This is the behavior of light. Light or any wave spread out in all possible direction. Now comes the concept of polarization. If I restrict the oscillations in one direction, I do not allow the wave to spread out conventionally, I will call it polarization. So what is polarization? It is the restriction of a wave in one direction only. You might have seen
Hello,
those
sir.
Yes. You might have seen those spotlights, those Polaroid camera lights, which are specially designed to improve the quality of the photography. So also famous Polaroids are used underwater for underwater photography because of their capacity of holding the light in one direction. So this is the first concept. You have to copy this. I'm just coming, copy this screen.
Done.
This is polarization of light. When light is traveling through a medium, it's a grid. You can notice that other oscillations are restricted, and now oscillations are restricted on one plane only. So write under it that polarization is a process. Polarization is a process in which oscillations in a wave polarization is a process in which oscillations in a wave are confined in one plane only.
Done, sir.
So this will be the definition of polarization. This will be the definition of polarization. Polarization is actually a process of optics. And if you people have a taste of using optical devices, the most common is a camera. Nowadays, there are many cameras in use. But I'm talking about those professional cameras which are adjustable, not talking about mobile phones. We use Polaroid there. So polarization is actually an optical technique. Polarization is a character of transverse transverse waves longitudinal waves can't be polarized. So you cannot polarize sound waves. You can polarize light waves. You can polarize water waves. You can polarize only transverse waves.
Done, sir.
Give the heading Mole's law. So Mole's law is used to calculate the intensity of plane polarized electromagnetic wave. What is the concept here? Again, it depends upon the exposure. When you are using a Polaroid, like underwater cameras, use that, or you have an outdoor shooting, you are on a hill station or on a long big landscape, you want to take a good picture, you need these polarizers. But the problem is that when you stop, suppose there are suppose 7 oscillations, you cut off or you retain only one of them, you will actually lose energy also, because wave transfer energy in all direction. When you confine a wave, when you confine a wave, you lose intensity also. So polarization of a wave decreases its intensity. Why? Because every oscillation in a wave transfers some energy. Every oscillation of a wave transfers some energy. So write under it that polarization tends to decrease the intensity of a wave. Copy this, and we are stopping here. We will continue in our next class, inshallah.
Okay, sir. Assalamu alaikum.
Wa alaikum.